Welcome to the final part of Lesson 13. We have now almost finished our discussion of normal stress differences and of their effects. In the last part of this lesson, we tried to gain some intuitive understanding of the Weissenberg effect and of extradate swell by thinking about the impact of a non-zero first normal stress difference. Whilst this was a useful mental model, we saw that the second normal stress difference is also involved in these effects. What we're going to consider now, however, are flow effects that are caused solely by second normal stress differences. We will see that some quite subtle yet significant flow patterns result from the presence of a non-zero second normal stress difference, and that these flow patterns can significantly enhance things like heat transfer or mass transfer in ducts. So let's try and think about how this might work. We've seen so far that the effect of normal stresses can be seen very visually, for example in extradate swell or in the Weissenberg effect. And in both of these we can see there's a definite change in shape in the fluid geometry because the fluid geometry is unconstrained at these points. An extradate can swell in free air and a fluid can climb up a rotating rod, again in free air. Now we thought about these in terms of N1, which is not entirely correct, but it's quite a useful means of intuitively trying to figure out what's going on. But what we're going to do now is look at N2 on its own and see what it can do. Now, our starting point is going to be thinking about confined flows, because this is where we see the effect. And we're going to think, to start with, of the simplest confined flow, which is a pipe flow. And we're going to revisit our normal stress differences and see what it is they're doing in this flow. So here on the board I've put a sketch of a flow in a pipe. There's my velocity profile, my flow direction is a z direction, and my flow is changing in velocity in the radial direction. That's my gradient direction. So if we think about our first normal stress difference, we've got tau zz minus tau rr, and that's my tension in the streamlines that we've been talking about. Now, let's look at plan view of this pipe. There we are, there's the pipe in plan view. And we can see now that we've got contours of constant velocity in this pipe. Those are those yellow circles there. And if we track around one of these contours of constant velocity, we're tracking around in the angular direction or the theta direction. And of course, it's in this direction that we get our second normal stress difference manifesting. So if we think of our second normal stress difference, let's look at an arc of fluid and look at how tau rr minus tau theta theta works. And we can see that there's going to be some effect here perpendicular to the main flow direction. So let's stick with the pipe to start with and think now in terms of forces. We're thinking in terms of normal stress differences to start with, but those normal stresses are going to result in forces. Forces will act to cause an acceleration, which means that if we've got a force imbalance anywhere, where we've got a net force that's non-zero, we're going to see some flow happening in a plane that is transverse or 90 degrees to the normal flow direction. So let's start by thinking about a pipe flow. So here on the board is my sketch of a pipe again in plan view. I've got my radial direction there in blue and my circumferential direction there in purple. So I'm going to place three elements of fluid at equal radius in different parts of this pipe in terms of angular position. So there they are in yellow. And I'm going to think how the normal stresses due to the second normal stress difference act. So let's sketch those on. I've got my radial normal stresses there in blue and my circumferential normal stresses there in purple. Now, the question we want to ask is there going to be any net force? Is there going to be a non-zero net force? So let's think about the lines of action that these forces would act upon. So let's think of the radial direction first. And if we project where a resultant force might act, they're going to be along lines of radii. And we'll see that they'll just cancel out. Because if we think about that right-hand lump of fluid, in exactly the same position at the same radius on the other side of the pipe, there's going to be forces of equal magnitude opposing that radial force. So the net force is going to be 0 in the radial direction. Let's think circumferentially, and again we can see that all these purple forces in the circumferential direction act on a circle at constant radius, that dashed line. And so there's going to be no net force. We can think about this yet again for another set of fluid elements, maybe at a different radius, and again all the radial forces are going to act through the same point as before, the centre of the pipe, and cancel each other out. And perpendicular to that, we've got our circumferential forces, and they all cancel out along a contour of constant velocity, which is just a circle centred in the centre of the tube. So we can see that for a pipe, for a circular duct, all the forces that act radially pass through the centre of the geometry, and all the forces acting circumferentially act along these circumferential lines and cancel each other out, which means that for a circular duct there is no net force, there is no motion perpendicular to flow direction that is caused by our second normal stress difference. So a circular duct is a nice simple geometry, the simplest geometry that we can think of really. What happens, however, if we move away from something circular and look at something square instead? So imagine what we have is a square section duct, and we've got flow along the long direction, in this case I've marked it as the x direction, of this square section duct. We remember that our second normal stress difference, N2, is proportional to my shear rate, which is going to vary along that cross-sectional plane, because my shear rate is the velocity gradient plus the transpose of that velocity gradient. So if we can figure out what the velocity gradients look like in that transverse section, we can work out the shear rate, and then get a bit of a sort of a mental model as to what's going on for our second normal stress difference. So let's look at this duct end on. There it is, square sectioned, and let's see what pattern of velocity we might expect. What sort of velocity profiles are we going to have? I've drawn those on the board there. There is actually a solution to the Navier-Stokes equations, okay, for Newtonian flow, that you can derive. It's a series solution that allows you to predict the velocity pattern in a square duct for laminar flow. And that's what I've plotted there on that graph. So these would be the contours of constant velocity going down this square duct. So we know what our velocity profile looks like, assuming constant viscosity. And actually there are a class of viscoelastic fluids that do display a constant apparent viscosity. They're called Boga fluids. So we're kind of doing a Boga fluid analysis here. If we look at the shear rate that this velocity profile infers, we see quite an interesting pattern. So there on the board are contours of constant shear rate in that square section duct. At first sight this might seem a little complex, so let's talk through it. At each corner you've got zero shear rate. In the centre of the duct you've got zero shear rate. At the midpoint of each of the four walls you've got maximum shear rate. It's sometimes easier to get a picture of this by looking in 3 dimensions, so let's just put a 3-dimensional plot of those shear rates on the board. There it is, and we can see far more clearly here that we've got, again, zero shear rate at all 4 corners and in the centre, and then those maxima at the midpoint of each of the 4 walls. So let's go back to my contour plot. So there are my contours of shear rate. Let's make the assumption that my second normal stress difference again is proportional to shear rate, and think about fluid elements at different points in this geometry. Let's start off by thinking about fluid elements at those points of maximum stress, at those midpoints of the walls. We can see that N2 here is going to be our biggest N2. We've got a X direction acting and a Y direction acting stress. And if we think about a fluid block again at the midpoints of the other 2 walls, in this case the vertical walls, we see the same pattern. And we see that the inwards pointing forces all go through the middle and hence cancel out. Okay, fine. Let's think, however, what happens at other points in this duct. Let's think of the corners first. We know at the corners we actually go down to 0 shear rate right at the corner. And so as we approach the corner, we'd expect our shear rates to be a lot less. Hence, we'd expect our normal stress difference to be a lot less, which is why I've drawn this with smaller arrows. If we think about the centre of the flow, again, we know our shear rate drops to 0 at the centre. It's where our maximum flow velocity is. And again, we would expect the normal stresses to be smaller. So this actually starts to paint quite an interesting picture. We can see that if we draw the symmetry lines on this square section duct, we've got symmetry lines joining the corners together and joining the mid-sides together, we can see the same stress pattern repeating itself. And if we think about one of these sections, let's look at the top of the diagram. Let's look at the right-hand side where we've got that big green arrow pointing to the right and that little tiny green arrow pointing to the left. There's going to be a net force resulting from the imbalance between those two fluid elements, which must mean there's going to be motion. Force is mass times acceleration, after all. If we've got a net force, we have to expect acceleration, we have to expect fluid motion. Now, the ultimate analysis of secondary flows in non-circular ducts for viscoelastic fluids is a bit more complex than just considering N2 alone. But by just considering N2, we can see that something's not quite right in terms of our force balance. There is a force imbalance, so therefore something has to result from that. I'll point you towards a reference to read later on in this lesson where it gives the complete picture of deciding not only where the force balances exist, but in which direction they act. But for now, we recognise the fact there's a force imbalance. If there's a force imbalance, there's going to be motion perpendicular to the main flow direction. Let's sketch out what that looks like. Let's look at my cross-section of my square section duct. Let's draw on my symmetry lines there in yellow, joining each corner and joining the mid-sides. And in each of these symmetry segments, we get a vortex. And usually we find that fluid migrates into the centre of the flow along a diagonal and out towards the walls along one of the symmetry lines joining the wall midpoints together. And so in a square section duct, we actually get 8 vortices, the direction of which is planar to the main flow direction. And this is why secondary flows enhance heat and mass transfer. Because if you think about it, what we're doing is we're removing material close to the wall and putting it in the core of the flow. So if our wall is hot, we're removing heat from the wall and putting it in the core of the flow. If the walls of my square section duct are a membrane and we have mass diffusion through those walls, we're removing material from the walls and putting it in the centre of the flow. So we've got an extra means of convection in this flow, which enhances heat transfer and enhances mass transfer. So if we think about the secondary flows you find caused by a second normal stress difference in non-circular ducts, typically, but not always, the flow is from the high shear rate region to the low shear rate region. And the full explanation of why it isn't always like that is in the paper reference I will give you. We can also see, as we've discussed, that you've got convection now in a plane that is perpendicular to the main flow direction. So heat transfer and mass transfer both benefit from this extra circulation. So here's the reference to look at. Yu et al., Journal of Rheology, 52 volume 1, back in 2008. Very, very interesting paper, very elegant analysis, and it also details some of the interesting effects that secondary flows can cause in polymer processing operations, distortion of multi-layer films, for example. And so that gives a very clear insight into the importance of these secondary flow effects and understanding how they manifest. So let's wrap up with a few key points. We've seen that second normal stress differences cause secondary flows in non-circular ducts. We've seen that these secondary flow vortices are in regions of symmetry, and we've discussed the fact that these secondary flows can enhance heat transfer and they can enhance mass transfer away from the walls of these ducts, and also they explain certain instabilities when you're processing multi-layer films in extrusion.